My name is Jesse Stutts. This is my ECE Exploring Electronics project. My application of interest is a drone ESC, which is an electronic speed controller. It is used to maintain stable flight by reading control and sensor inputs and modulating the speed of each motor accordingly. The way it modulates the speed of each motor is pulse width modulation. So in this case, we have a permanent magnet DC motor. This is a three-phase motor. As you can see here, the permanent magnet is polarized north and south, and in this particular case, rotating clockwise. With this orientation, this stator, this coil is charged such that the North Pole is adjacent to the North Pole of the rotor, pushing it away. This one is energized the opposite direction so that the South Pole is pulling the North Pole across. Both of these apply a torque on the rotor, and with this orientation, this pole is turned off because it would not apply any torque at this location. But doing this, the way it works, you can only apply a current off and on. So the way it throttles is by doing that very rapidly. So this is the current and time curve at full throttle. You can see it's just maximum torque all the way. And here it is at partial throttle. And you can see over time, this current source is shut off and on very, very quickly. This frequency is on the order of kilohertz. So this is done extremely fast so that it does not jam up the motor, and the motor still runs smoothly because the motor itself is going, depending on the electric motor, possibly 12,000 RPM. So the pulse width has to be much faster than that while it is in the correct phase and orientation to get through this entire curve. So the way it does that is electronic engineering aspects of it. It is a PLC at its core. Pulse width modulation of the DC electric motor. That comes from signal amplification and filtering of the accelerometer capacitance. That is one of the inputs that it takes into that output. So looking at the accelerometer, it is a differential capacitor. So you have this mass right here that when the acceleration acts on it, it bends this flexible silicon beam here. And these have a known elasticity. So the acceleration is known from the beam deflection. And the way it reads that is with these fingers and these two separate sets of electrodes here. As the beams deflect, the fingers get close to one set and further away from the other. So you have two different capacitances. And that is why it's a differential capacitor. It's basically subtracting these two values instead of just reading one capacitive value all the time. And this capacitance is on the order of picofarads. So it's very, very small, which is where the signal amplification and filtering becomes so important. This whole device, all on its own, is also very small, about 240 by 500 micrometers. So extremely small, seemingly delicate, but they can handle large accelerations and accurate measurement. And my fun fact is that this dimension is the equivalent of 500,000 nanometers. The smallest microchip transistor gates are only 2 nanometers, which is 10 times smaller than the radius of the silicon atom that's made of at 0.2 nanometers. So we're really pushing the limits of what semiconductors can be as far as being made out of silicon. And even though this is an order larger, these flexible beams are still only on the order of thousands of atoms wide. So you're doing structural calculations on that and an even smaller order of capacitance all going into this one single, very small component.